Hello, my name is Pete, and welcome to another session of Electronic Assisted Astronomy with an 8-inch Schmidt Cassegrain telescope. It's summer, and even though the island is a subtropical paradise, its latitude of over 50 degrees north assures us of a constant glow from the sun, which sits just below the northern horizon. In fact, our last dark night was back on May the 12th, and we don't see astronomical darkness again until the 29th of July. Due to the location of the Sun, low Earth-orbiting satellites are running amok across our field of view. However, our saviour is Stellarium Satellite Plugin that provides us with early warning of these photobombers. We're using the active and analyst TLE data from Celestron to keep track of nearly 10,000 satellites. Tonight, we're going to observe a favourite type of object of mine, globular clusters. These mostly ancient and tightly packed glowing balls of stars have been with us since the first stars clustered together. A majority swarm around our galactic halo, dipping in and out of the galaxy's plane as their million years orbits unfold. We are using the Celestron CPC 800 f6.3 with the ZWO ASI 523 mono camera and a SkyWatcher moon and Skyglow filter. For tonight's session, we have dark and flat calibration frames, with the dark frame being assisted by SharpCap's hot pixel removal feature. The subs are 4 seconds, the offset brightness setting is 70, and we're using the blended offset background subtraction. We're also dithering every 6 frames. Okay, let's get live stacking. So M13 or NGC 6205 lies in the constellation of Hercules. It's got an apparent magnitude of 5.8 and is around 20 arc-minutes in size. Tonight I've got 2 SharpCap enhancements turned on. We have the bilateral noise filter and the Wiener deconvolution. Now the deconvolution filter seems to be very well suited to globular clusters. It really improves the view. On the astrometric side, M13, as it lies at a distance of about 22.2 thousand light years and has a radius of 84 light years. It's a pretty amazing sight, even after a few frames. So I really want to stretch the image to bring out all those fainter stars, but I think I'm going to need to stack more frames to reduce the noise in the image. We're only doing 4-second subs, so I think the noise is going to reduce quite quickly, and the bilateral filter helps as well. In fact, while M13 is stacking, why don't we explore M13 a little closer and some other tools. So we're using Stellarium as our planetarium program, and it is amazing, but its star catalogue is limited to only 177 million stars. That's more than enough, you might say, but when viewing globular clusters, we need to bring out the big guns, I think. In this case, the Gaia DR3 star catalogue. Now it has 1.8 billion entries. Now for this, we're going to use the free planetarium program, Carte du Ciel. So this is SkyChart. Now, I don't believe that SkyChart is as pretty as Stellarium, but it does have a lot of functionality and a lot of history to it. Right now, we've selected M13 NGC 6205. You can see it right here in Hercules. And let's zoom in a little bit. We'll zoom in to 1 degree. And as you can see, these are the stars, but that's only really the start. As we moved in, we will keep on seeing more and more stars. And these are all in the Gaia catalogue, just huge numbers of stars. And the great thing is we can just pick one, double click on it. And here we have information on its proper motion, the parallax, which allows us to calculate the distance. In this case, it's considered to be 30,000 light years away, that particular star, and a load of other information. But this is the main information that's coming from Gaia. So SkyChart does all this free of charge. You can download it. So if I show you the catalogues. So as you see, the author has broken the Gaia download, which is quite large. The largest section is 39 gigabytes, which expands to 54 gigabytes on the disk drive. But he's broken it down into 4 parts based on the magnitude range from 12, 15, 18, and then up to magnitude 21. So you just choose which level you want. In this case, this is all of the levels up to magnitude 21. And with globular clusters, it is quite amazing. And all of this is free, of course. Now, there is another tool which allows us to take that information that Gaia's generated on distances, and we can kind of see where this object is in space. It's called TOPCAT, and we're going to use a catalogue that's been processed from Gaia data to give us the actual distances in kiloparsecs, I think, but we might convert that to light years. So this is TOPCAT. TOPCAT stands for Tool for Operations on Catalogues and Tables, and is written by a gentleman called Mark Taylor from Bristol University. Now, this tool is far out of my league. It's obviously designed for scientists to explore sets of data, and it seems an extremely powerful tool. But I'm going to use it just to show three-dimensional space for these stars in M13. So what we're doing here is a cone search. So I've put my object name in M13. I resolved its location in the sky. I want a radius of 0.5 degrees. And I'm going to bring back all the objects which are in the Starhorse 2 Gaia EDR3 Photo Astrometric Distances catalogue. If I press OK on that, they've been retrieved. Fantastic. So what I'm going to do now is, because I want to show the distance in light years, I'm going to show you first of all the table. In fact, we just zoom in on the table. So these are all the columns, and the column we're interested in is this column here, distance 50, which is in kiloparsecs and is the distance 50th percentile. I'm going to add my own column called, light years, I suppose. And we've got an expression which we can put in where I can take that distance 50, which is in kiloparsecs, convert it to parsecs by multiplying by 1,000, and then multiply again to get it in light years, and the unit I believe is LY. And I'll add that into my data. Let's come back out again. And in TOPCAT itself, I now do a 3D plot. Let's make this a little bit bigger. And we're going to change the X to RA, the Y to the declination, and we're going to find on our new calculated light years column. Oh, there it is down there. And there we go. So now we're plotting distance. It's a little bit strange, but we will try to see how we can do this. So we've got RA and declination here and light years here. If we spin that around, it's a bit of a game, a bit of a cubic Rubik cube, should I say. There we go. So what I'm going to do is, if I go into my axes and go to the range, I'm going to pull the range down, and as we pull it down, you may notice that a disk of stars starts to appear. In fact, here it is, right here. And this is M13. Now there's a cone of stars that comes out this way and a cone that comes out this way. And my hypothesis is that because the stars are so crunched together, that maybe Gaia has errors because one star might overlap another. And of course, that's all taken care of in the processing. And I know they're doing something for the data release 4 for areas like this, which are very densely populated in stars, to get better positions. I could also be talking absolute rubbish, of course. But it's quite interesting that right there is a disk of stars. And what I'm going to do is I'm just going to quickly, very roughly, just select those stars. And it's going to be very roughly. You have to excuse me the odd 1,000 odd light years I was probably taking in here. There we go. So I've selected it very roughly. I'm going to call it M13 because that's what I believe it is. And so now I can highlight that, and that I believe is the location of M13 in three-dimensional space. In fact, what we can do is, if I go edge on, and we know that M13 is 22,000 light years away. If I take that blue disk up, that is 22,000 light years away. Just over 22,000 light years away, which is what we know it to be, because we know it's 22.2 thousand. So that's a great use of this little tool. I just found it quite fascinating. And I was trying it out on some other globular clusters that we're going to observe. And yeah, it's quite amazing to see the amount of information that Gaia holds. What I'll do is I'll put a link to all of these tools in the description. Let's see how the live stack of M13 is getting on. It's always interesting to see the rapid reduction in noise in the first few frames of live stacking, and then it's followed by that kind of slower revealing of details as the stack progresses. I'm going to leave you with some of the other globular clusters I observed during the session. Have fun.